Up next, we will hear from Kyle Morgenstein. What will it take to bring helpful, friendly robots into our homes? Kyle Morgenstein has devoted his graduate studies to answering this question. Using reinforcement learning, Kyle researches how safe and friendly behaviors can arise from simple axioms for humanoid, quadruped, and other mobile robots interacting with people. Specifically, Kyle seeks to give robots a sense of touch, allowing them to reason about the effects of their actions on the world around them. He is a fifth-year PhD student at UT Austin, advised by Professor Luis Sentis, and holds bachelor's degrees in aerospace engineering and planetary science from MIT. During his PhD, Kyle has collaborated with NASA JPL and the Robotics and AI Institute, formerly Boston Dynamics AI Institute. He will begin working with Aptronics in the summer of 2025. Please join me in welcoming Kyle.
Cool. Let's see. Thank you for that introduction. Can you hear me all right? All right, great. Thanks for having me. My name is Kyle. I'm a fifth-year PhD student, and today we're going to be chatting about humanoid robots and putting robots in our home spaces. I think over the last couple of years, we've seen a phenomenal amount of excitement and hype related to humanoids in particular. I think a lot of that started with industrial spaces, manufacturing. We've seen a lot of the investment coming from those environments. But in the last 6 months, it's felt like there's been a bit of a shift in a lot of the marketing and materials these companies have been putting out about their robots. In just the last 6 months, we've seen 3 different companies showing off robots in human homes. And I think it's exciting for a number of reasons, but I think it's also a large shift in the focus that as a research community we've had. For example, as early as this morning, we see a lot of videos that tend to showcase more of the capabilities of these robots. It's a phenomenally smooth video, but this is not something that you necessarily want in your home, or maybe you do, but not in a helpful capacity. And I think that when we see these kind of videos, we have a tendency to assume if we can do these stunts, then it must mean that we can also do, sort of simple tasks, pick and place, industrial tasks of that sort. And if we can do the Ronaldo jump, then why can't it put away my clothes? And as we've increased the capabilities of these robots, one thing that we really haven't focused as much on is the safety aspect. If we're going to put these robots into our home spaces, they have to be things that we want to interact with and we feel comfortable interacting with our children, with ourselves, with our belongings, etc. And so I think you contrast that messaging with this recent video that came from 1X. You can see both in the design language as well as in the hardware, this is a very, very different type of demo. They're not showing raw capabilities or phenomenal dexterity. What they're showing is a soft robot in your home doing the kind of tasks that you might want a robot to do. And to me, this marks a very big difference compared to what we've seen out of humanoid robotics in the past, and what I think is going to end up becoming one of the most dominant markets for them in the future, given that these form factors do fit so nicely into our home spaces. So you can see the very smooth manipulation. It's very clear what their vision is when they release these kinds of videos. So I want to talk a little bit about how we can teach these concepts of safety to robots. Throughout my PhD, I've worked on humanoid robots, quadrupedal robots, mobile bases, and I'll touch on all of those today. But I think the first core question is, how can we teach robots these sort of non-engineering metrics like safety? If my only goal was duty time, how fast can I do a task? That's something I can optimize around. If I care about how fast my robot runs, I can record that and optimize for it. Safety, we don't really have a good way of optimizing for it. We need to use proxies. And so there's 2 different ways we can do this. The first is by learning from demonstrations. I know what it means to be safe because I can do it and I can show it to my robot. This is fairly easy to demonstrate because I can just take videos of people doing it, but it's hard to generalize. If you put a robot in a sufficiently different environment, a different home, doing a different task, then these notions of safety may not transfer from putting away your fine china compared to putting away other types of items that you also don't want to break. Then we contrast this with learning from trial and error. The reinforcement learning is the class of methods here. And this is sort of has the opposite problem, where it's much harder to quantify what you mean by safety. You still have to have some optimization metric or proxy that you use, but it's much easier to generalize. It's easier to generate examples of doing these behaviors in different environments. And so we're going to focus more on learning from trial and error today because it's been the focus of my research. And so the idea here is we want to use very, very simple principles and try and get safe behaviors to arise without having to tell the robot exactly what we want it to do. And so in this case, the two principles that we give it are we would like to reach some goal state or configuration. Maybe it's putting an item away or navigating to the end of a hall, and we don't want to harm people. And as a very simple proxy, we're going to use contact force as a safety metric. So we would like to not violate some amount of force that we think would cause harm. We have a lot of studies from prior work showing what these thresholds should look like. We cut them in half and call that a safety threshold. So it's a fairly simple proxy to start. And we're going to use this in sort of the idealized setting. So here we've got a mobile base that we designed for a pediatric hospital setting. And in this, we have full state observation. We assume that we can sense our contact forces. We've got LiDAR. We've got depth cameras. Sort of any information that you want to know about this robot, we have access to. And our goal for this is to navigate through crowded hallways. And so if you use these two principles and you train in simulation a robot to do this task, what you see is that it has surprisingly complex behaviors even from these very simple principles. So it accelerates into free space, but when it sees that it gets near people, it slows itself down and makes sure to keep its contact forces below that safety limit while still navigating to the goal pretty effectively. And so then the question is, well, what happens when you don't have perfect information? So for example, what happens if the camera is occluded or gets smudged? And what we see is a totally different behavior. So the video will reset in a moment, but whereas before the robot would accelerate into free space and then decelerate when it gets near people, this robot, you can imagine if you woke up in the middle of the night without your glasses trying to find the bathroom, you're sort of tiptoeing and bumbling in the dark. That's what this robot is performing. It's never reaching a velocity faster than the speed such that if it made contact with a person, it would stay below that safety threshold. So as a default, the behavior is safe. It's no longer proactive. It can only respond reactively, but that reactive behavior is guaranteed to be safe by the thresholds that we've defined. And again, we don't tell it anything about how it should do this search or what behaviors it should look for. We just tell it, get to the goal and don't hurt people, and that's it. And even from that, we can get these sort of diversity of behaviors based on the information that the robot has access to. It can learn to reason about what information it has and what it doesn't know. Now, if you expand this to a robot that doesn't have perfect information, something like the Boston Dynamics Spot, and I promise this is the only scary method slide, we'll move past it in a moment, where we don't have contact force information, we need to estimate it in some way. And so we do this by fusing the control and estimation procedure. But what this lets us do is reason about contacts and balance in a way that's a lot more dynamic than you might be able to get without this kind of contact information. So here the robot is walking on a narrow plank, so it's already sort of difficult for it to keep its balance. But then it also is interacting with this punching bag that weighs more than the robot does. So it's quite a difficult balancing task. And it also is keeping its contact forces below that safety threshold. So we're saying that humans look kind of like punching bags in this environment. I hope that you'll allow for that. And so you see it sort of slows down before it makes contact. It ducks low to get its center of mass down. It's able to push it to the side and maintain its balance and complete the task. And in this case, it does have access to vision, but we don't give it the contact forces explicitly. It has to learn to reason about them on its own. Now we train it in the simulation environment where we're applying very strong kicks, the kind you're maybe accustomed to seeing from Boston Dynamics robots, but it can respond to very light interactions with a real person as well. So we have this robot here, and I have it bump into me, and this is in a manual control mode, so I'm telling it to bump into me and then to stop. And what we see is that just based on the data we have on board, it's able to estimate the contact forces, both with its feet and the ground, as well as with its body and me, very accurately. And it's able to do that in sort of any of these environments where you're navigating around people. And so we're able to pick up on how much force are we applying and is it within our safety margin. And so the claim that I want to sort of make and leave with is that reasoning about contact should be a prerequisite to putting these robots into our homes. That if we want to be able to include these robots in our home spaces, and I'm glad to have the booster here, it's where we've been teaching it to walk and run in various ways with the same kind of framework. If we want these in our home environments, then it has to be able to interact with us safely, and that means the robot has to know what it means to interact with us safely, and contact is sort of the most basic form of that. There's a couple additional benefits. For one, we get a more complete representation of our dynamics in the latent space of the policies. And more importantly, we can use it as a runtime metric for the safety of the robot. So for example, using something like a momentum observer, we're able to estimate the contact forces as sort of a ground truth signal, and we can compare that to the output from the contact estimator as part of the locomotion system. If those diverge, then it means that the robot isn't able to reason about its own contacts, and so we shouldn't trust its behaviors as much. So we can give us a rating of how safe the policy thinks it is as it's locomoting in our environments. And so we're hopeful that this will lead to a lot more considerations for safety that will make these robots fit better into our home environments. So we're excited for that. And I think with that, we have time for questions. Thank you. All right, I saw your hand.
You mentioned, sounded like the presentation more about contact detection. You mentioned maybe following, kind of teaching socially acceptable behaviors. Is there any plan to actually more like vision, if you're like following a human around performing a task, turning a valve or something? How do you take that video data?
Yeah.
Convert that into kind of movement for obviously it depends on if it's a humanoid robot or a quadruped. You need to have a dog moving the task.
Yeah.
Can you speak to that just a little bit? I know it's different than your.
Yeah, so again, to fit into this framework of sort of, we have our goal state that we'd like to reach, and then our safety requirement that it not hurt a person. Safety right now, we've defined it just in this contact sense, but you can also imagine perceived safety. Do I like the robot's behavior? Is it following too close to me or too far, et cetera? And so there's different methods we can use, like inverse reinforcement learning, where we take data from humans doing similar tasks, and as opposed to trying to imitate that data, we instead can try and extract a reward signal thinking, what is the human thinking about when it performs these behaviors, and then try and match that reward distribution for the robot. So it's, as opposed to trying to match the behavior explicitly, we're trying to match the sort of value function that humans use when we decide what's a good or bad, a safe or unsafe action. Cool. So here.
When you're trying to generalize outside of contact forces, it's trying to follow the idea of not harming a human. How would that look like? Or I mean, I know this is not specifically what you've been researching lately, but how do you generalize beyond just contact? Like maybe there's a knife in the kitchen, and it's very dangerous if you pick up a knife and throw it around.
Yeah.
How do you go beyond the generalization of this contact?
Yeah, so I think there's an easy answer and a hard answer. The easy answer is we also do a huge amount of user studies with all of our robots. So beyond just is it making contact, but when we have it in a hallway or in a hospital or in your home, we're then getting both qualitative and quantitative information about how the people feel interacting with our robots, completing their tasks. And then we use that as a feedback loop to then bring it back into our reward structure of, okay, this was a thing that the robot did, the people didn't like it, it didn't make contact, but we got gathered data that they didn't like it, and now we can design a reward according to that. So there is a feedback process there. The harder answer is that we don't really know yet. There's a lot of things, like you mentioned, like, sure, the robot is chopping vegetables and I feel safe because I've seen the robot do it 100 times and it's okay. Sure, the robot could decide to turn and throw it at me, but I don't think that it will because it hasn't ever learned to do that before. I think that's similar to the first time you get into a driverless vehicle, it's very scary. I know for myself, at least, I was very nervous. But after I did it for 3, 4, 5 times, I stopped really thinking about it as a scary thing because I learned to rely on the system. Similarly, like, yes, in theory, the robot could pick up a knife and stab me, but as you spend more time with these robots and figure out how they're thinking about the problem, it's not a thing that I think people will worry as much about.
This may be a bit of a silly question, but in the space of like actual research for robotic safety, do you guys mention Asimov laws at any point, or is it just more like a perk or like a sci-fi thing?
More of a sci-fi thing. It's not something that we embed into our research in any way. No. Yeah. Any others? See you in the back.
Are there any particular standards that are established to validate across the different people that are doing this?
Yes and no. Phenomenal question. So in the cobot space, we've got robot arms that are no longer in cages. There was a sort of big push in the standards community to go from the types of standards that were set in sort of the previous industrial robots where you had big cages, very dangerous, don't touch it, to now these robots that could both sense contacts and torques, and we could also interact with physically. And we're starting to see some work in the standards community to make the same kind of transition from those fixed robots to mobile robots that can interact with people. And so there aren't currently standards for those, but we work with standards committees to try and build those sort of expectations. For example, for the hospital robot, we're working with the FDA to set those sort of standards that we hope will be industry defining in the future. But there do not currently exist standards for these sorts of robots as it stands today. That's something we're working towards.
Thank you so much, Kyle. That's all the time we have for questions.
Thank you.
Up next, we will hear from Arthur Zhang. Arthur is a third-year computer science PhD student in the Autonomous Mobile Robotics Laboratory and is advised by Professor Joydeep Biswas. His research interests are broadly in representation learning and robot navigation in urban environments. Arthur's prior research includes novel methods for representation learning from visual foundation models, generalizable 3D object detection, and real-time 3D semantic mapping. Please join me in welcoming Arthur.
I'm going to switch this up. Yeah, so I guess while we're setting up, I'll give a primer for some stuff I'll be talking about. Kind of like Kyle mentioned earlier about inverse reinforcement learning. Our work will talk about some of that and how we use that to basically align the robot navigation behavior with human preferences. Okay. So, yeah.
Where is your presenter view on this?
Yes.
Is that it?
Perfect. Is that?
Okay,
Great.
Cool.
Can everyone hear me okay? Yep. Great. Yeah, so today I'll be talking about a recent work called CREST, which is scalable mapless navigation with internet scale priors and counterfactual guidance. And first I want to take a moment to thank my collaborators, whom I have listed here. So the problem that we're motivated by is general purpose outdoor mapless navigation. And this problem is quite simple. Given some location that you start at and a goal that you want the robot to reach, can the robot navigate there fully autonomously? And lately, you may have noticed a bunch of sidewalk delivery robots, and maybe you've noticed that they're maybe no longer there. I'll get into a little bit about why that's so challenging and what we're doing to address that. So there's many challenges that you face when trying to navigate outdoor in sort of a general environment. One such challenge is even when you're navigating on sidewalks, there's these sort of edge cases or long-tailed cases where it's very difficult to robots to reason about them in traditional ways. So here we have a robot getting stuck on the branches of a tree trunk, which are actually quite difficult to see. And in another case, we have this robot that's unfortunately getting smashed by a car because it's not able to predict that the car will actually collide with the robot in the future. And even in navigation with pedestrians, we notice that this is a big problem with robots unable to deal with pedestrian dynamics. And so these are all pretty difficult challenges. And you might ask yourself, okay, I've seen lots of self-driving vehicles, and they're doing a great job navigating around. As Kyle's mentioned, they're actually pretty safe. And you might ask yourself, why can't we do that with these robots? Well, one key assumption that these methods rely on is having this high-definition map. And what they use this map for, as I'll show here in this video, is this bird's eye view of a high-definition map for which the robot can use to basically figure out where it is on the map and also figure out where it needs to navigate to. And this is very helpful for making these methods more robust. Case in point, this is actually a demonstration from a robot we have navigating on UT campus for half a kilometer with dynamic objects completely without interventions. However, even though these give us lots of benefits, they require constant maintenance to construct these maps, and each time you deploy a new environment, you have to create this oftentimes with human supervision. So, the natural question is, can we do better? And we believe so. We believe that similar to what these methods are using with just low-cost GPS, onboard sensors such as an RGB camera, and course guidance from any routing service like Google Maps, we can achieve similar performance to if you had this map. So now I'll talk a little bit about prior approaches to doing this, and I'll kind of breeze through this because I want to get through my stuff, but I think this will be important. So people have tried basically designing clever ways of representing the world, but the difficulty about doing that is that this doesn't generalize to the long-tailed cases that these robots fail in. To try and go beyond this, they'll try and learn representations about the world that either care about terrain, as in the top image, or elevation in the bottom. However, these methods, they fail to generalize to novel terrains or elevation or factors that you didn't previously consider. To extend that, people have tried just learning both the representation of the world and also how you should behave completely from expert demonstrations, so what humans would do. However, these methods require really large-scale robot data sets, more data than we can possibly have access to currently. So the one thing you might have also noticed is that we have ChatGPT, which is really good. Can we just directly use something like that for navigation? And we actually found that if you directly try and apply this for the task of mapless navigation, they actually perform quite poorly. So yeah, now I'll introduce CREST, which is a method that learns generalizable representations of the world and also rewards for the full mapless navigation problem. And so we overcome many of these limitations from the previously mentioned. Our method is able to learn these representations without dense human labels, without exhaustively enumerating what you expect to see in the world, and without large-scale robot data sets. In addition, we're able to align our navigation behavior with human preferences without having to require experts to basically design what the robot should do. A normal person can demonstrate what they want the robot to do and what not to do, as I'll get into, and that will be enough to align their behaviors. So our work has two key ideas. First one is representation learning through model distillation. This comes from this observation that nowadays you have these really great visual foundation models that can do things like segment images or tell you what parts of images belong to what body part. And these are trained on large internet scale data. And so the question is, what we propose this way of distilling these rich navigation priors or information from these models into a bird's eye view representation that we can then use for navigation. The second key idea is that, as mentioned before, many prior works, they use expert demonstrations to basically learn robot behavior that's aligned with human preferences. However, we've actually found that that guidance is pretty poor, and you can actually do a lot better if, in addition to providing expert demonstrations, you have counterfactual demonstrations. So you might ask what that is. Here in this image, I have a bird's eye view as well as a front view image where the counterfactual demonstrations are in red. So these are essentially demonstrations that show behavior that is misaligned to what we want the robot to do. And just by using this with our objective, we can actually learn much better robot behavior that's aligned closer with our preferences. So now I'll talk a little bit about our approach. The first step is our model takes in an RGB and a sparse depth image, optionally, and then it learns to predict some image features for the world, as well as the depth that it sees. Then what we do is we lift these features of the world into 3D, and then to make it easier to process, we then splat them to bird's eye view. Then what we do is we distill more priors from these visual foundation models to actually ground this in bird's eye view. And finally, we gather some expert demonstrations, we gather some counterfactual demonstrations, and then after selecting some of that, we train our reward function to be aligned to doing what experts would do and also not doing what experts wouldn't do. And then we predict this bird's eye view reward map that we can use for navigation. So as you can see here, we're generalizing really well to several challenging scenes, such as navigating complex sidewalks, driving on sidewalks in which you can barely see it because it's covered by foliage, dealing with avoiding things like crashing into strollers, which we've never seen before, and navigating tight spaces with pedestrians. So now I'll talk a little bit more about this with some results for some quantitative experiments. So we did this on many different environments, all in urban spaces with this mobile robot that you see here. And notably, we did this with just a few hours of demonstrations, which in comparison is over 10 times less than any comparable existing method. And we primarily evaluate how well we're doing by seeing how long we can drive or how far we can drive before an intervention. We compare against a few state-of-the-art results. These results range from the methods I talked about earlier that consider the geometry of the world and things like that. And we answer the following questions in our full paper, but for the purposes of this talk, I'll focus on these two, which is answering how well our method does for unseen, so new environments, and how well our method does like long horizon, kilometer scale navigation. So here I have a plot showing the distance driven per intervention of our method, shown in red, compared to existing approaches. And I also have the total distance driven as well. So basically, if our bar approaches that total distance driven, that means we're doing really well. And you can see, in comparison to a lot of existing methods, we're doing really well with 2 times fewer interventions than anything else. And you can see this pretty clearly in some of these results here, where this left one is showing a result using a handcrafted representation. So you're just using geometry to figure out what to not collide in. And you'll notice that this is running into many problems, such as colliding into curves, similar to the tree trunk example, that are difficult to deal with. In this next one, we're considering both the terrains to make sure we only stay on the terrains that we'd want to drive on, as well as geometry. However, the issue with these methods is that they don't leverage this internet scale prior from these visual foundation models. So when you encounter classes that you haven't seen before, or lighting conditions are suboptimal, they perform poorly. And in contrast, our method is able to deal with things like navigating on narrow sidewalks, finding the correct curb gaps to go up when crossing roads, and also dealing with pretty heavy lighting artifacts. So up next, you'll see us dealing with heavy shadows and things like that, even though we haven't necessarily seen them in this environment before. And then one thing you might ask yourself is, okay, you're using RGB images and LiDAR, Well, lots of these LiDARs are really expensive. Can you do this with just RGB images alone? And we actually find that you can. So this plot is showing how well you can perform with just RGB, which is this second bar, versus RGB plus LiDAR. And we find that the performance is actually pretty comparable. So here in these next 3 examples, I'll highlight a few of the downsides of just RGB. You can see there, it's affected by heavy lens flares, for instance. Whereas for LiDAR, this is unaffected by these environment artifacts. So while you can achieve more robust performance with these additional sensors, they're not actually required to do pretty well. And you can actually see there in this last example, that's one of the limitations I'll get into next, where when you're dealing with navigating around pedestrians in really tight spaces, this is something where you have to negotiate how you should navigate. And that's actually one of the limitations of this style of approach. However, this is an existing limitation we've known from before and that we plan to tackle. In this next video, I show this long horizon 2-kilometer deployment with Crest, and I show a portion of it, because if I wanted to show all of it, it'd be too long for this talk. But you can see it's really gracefully dealing with lots of complex things that we haven't seen in the trained data set, and doing pretty well. So now I'll talk about the limitation. So as I mentioned before, navigating around people is still a challenge that's difficult and that we have yet to address. In addition, our representation is learning what you should traverse in a way that's aligned with human preferences, but oftentimes you want to reach different types of goals. Maybe you want to specify goals that are reaching a GPS location. Maybe you want the robot to more like explore the environment or locate an object for you. These are all things that we'd like to be able to condition a representation on for the robot to natively learn how to recognize. And finally, there's a lot of talk about humanoids, and I think one open question is, how do you learn a good representation that works well for navigation and also for manipulation as well? And that's a big problem that we're looking into as well. So thank you for listening. If you're interested in checking out more of this work or looking at the paper, we have a QR code at the project website here, as well as if you want to watch the full uncut video of us navigating around Mueller, you can scan that code as well. So yeah, thank you for listening.
Hi. What are your plans for handling the negotiation with the pedestrians in tight spaces?
Yeah, that's a great question. I think one key thing here is that our method is only considering estimating this from a single image, right? And to understand pedestrian behavior, you need to be able to do some level of forecasting about what the pedestrian would do. But actually, one thing that's more fundamental that many methods neglect is actually assuming that the robot's actions don't affect what the pedestrian's behavior will be in the future. I think that's a pretty big open challenge. Trying to, one, come up with ways to actually train a model to do that, because this would require having an accurate model of pedestrian dynamics, which is actually pretty unpredictable. So, yeah. Sorry?
What are you doing with all the data that you're collecting?
Well, so some of the data that you saw here, we use to train the robots. And a lot of the, well, one thing that we're thinking about is all of us are collecting all of these individual robot data sets for our experiments. Is there a way to basically aggregate them and use them for more of a large-scale training? So you can imagine with methods like these, they tend to scale well with data. So the more data that you have, the better they'll get. However, one limitation is that many of these methods require many prior information that is not common. So some methods require having, let's say, densely labeled images with what every pixel in the image corresponds to, or depth. So we're trying to develop methods that don't have to rely on all that, which is what this is going towards. Yes?
Yeah, did you find the visual foundational models that you're using are decent enough at like just out of the box for the environments that you're working with, or do they require fine-tuning based on additional images or retraining those models based on where you're deploying it?
That's actually a great question, and I have a video here that I skipped over, which astute people have seen. So in this left video, I have a model that's taking an out-of-the-box visual foundation model, completely untrained, frozen weights, and all we're doing is we're using this to navigate, we're we're grounding the features from this foundation model to bird's eye view. So we're still doing some training for a different part of the model, but it's not for the part that encodes the RGB images. And I guess backing up one bit, I show that in this table here. The bar on the left is actually that method. So you can see that while this method, using those models out of the box, can give pretty good performance, you can see the performance, the number of interventions is actually reduced by, I think, nearly half in this case. So by basically by distilling these navigation priors from these models, but also not learning things that don't apply for navigation, we can actually achieve better performance. Yeah, and I guess I'll show this video in the background too. So the one on the left is the one that's using the frozen visual foundation model, and the one to the right of that is using a distilled version, but using the exact same inputs. So you can see they perform pretty similarly here, but aggregated over many trials, you start to see the performance gap. Yeah. Yes.
Are you performing this in real time as you're going through the pathways? And are you computationally limited in any way to achieve these calculations?
That's a great question. Yeah, I mean, when you're navigating dynamic environments, that's very important. And that's one of the key reasons why instead of just using a visual foundation model, we distilled one. So our model is actually running at 20 hertz, just using the onboard compute, including the full navigation stack. So this is running basically a mini desktop computer on the robot, but the robot itself is quite small. So all of this is happening on board, real time, and it's doing, I guess, closed loop, adaptation to dynamic entities. Yeah.
Thank you, Arthur. Up next, we will hear from Siddhant Agarwal. Siddhant is a third-year PhD student in the Computer Science Department, working with Professor Amy Zhang and Professor Peter Stone. His research interests are unsupervised reinforcement learning, representation learning, and goal-conditioned reinforcement learning. He has been focusing on leveraging award-free data to learn representations through principled algorithms to efficiently produce policies for a wide range of tasks. Please join me in welcoming Siddhant.
Okay, so hello everyone, I'm Siddhant. I'll be presenting my work on proto-successor measures, which is about representing the space of all possible solutions of a dynamics model of reinforcement learning, like anything. This was a collaborative work with Harshit, Peter, and Amy. So let's start with sequential decision-making problems. Most of the problems that we try to solve in the real world are in some way sequential decision-making problems. You see an observation, you make a decision, you execute that decision, you see an outcome, based on the outcome, you make another decision, and it goes on. And such problems range from like robotics to navigation to games to even like solving math problems. You make a choice of you make something a choice and a step while solving a math problem, and that's also a sequential decision-making problem. So I'll introduce reinforcement learning as a tool to solve sequential decision-making problems. Now, putting it formally, we have an agent, we have an environment. The agent interacts with the environment by taking like actions, and the environment provides the agent with a state and a reward, or a reward which is a scalar value telling how good that particular action decision was of the agent in context of the overall goal of what the problem is all about. There are certain assumptions, the traditional Markov assumptions, that the policy, the transition dynamics, and the rewards only depend on the current state and action. So reinforcement learning, in principle, does not try to solve all sequential decision-making problems, just a subset of them where we are having this Markov assumption. And finally, the objective is to find a policy that maximizes this cumulative sum of rewards. Now, we can have an environment where we can have several tasks in an environment, and mathematically you can sort of define infinite rewards, infinite tasks in an environment. Just consider, say, a robotic arm. A robotic arm can do a lot of things. It can pick and place. It can open a drawer. It can open a microwave. It can do lots of manipulation tasks on the same dynamical system. Similar with navigation, as you could, like I showed a maze here, but you can have like any real-world navigation system. You can have as many tasks, as many rewards as possible. It could be different goals, it could be different waypoints, it could be different costs that, okay, you shouldn't take a particular route, and you can define as many tasks as possible. And similarly with a humanoid. In a humanoid, you have the same system, and it can run, it can stand, it can jog, it can do a whole lot of acrobatic skills. Now, training single RL agents for all of these tasks is not feasible. It's very expensive. Training RL for even one task is pretty expensive. Also, because as the number of tasks increase, and often you don't even know the task that you will be solving in the dynamical system, it's infeasible to collect expert demonstration for all these tasks. So how do we solve solve such a system where we can have sort of infinitely many tasks defined on the system? This brings us to the regime of unsupervised RL. Now, as a human, if I do a task in an environment, doing subsequent tasks keep getting easier. Also, if I explore an environment once, it's generally enough for me to solve several tasks in that environment. Obviously, the question is, have I explored enough? Is the task within the things that I've seen? How much do I recall? But in general, as a human, I can solve a variety of tasks by exploring once in the environment. Can we instill this ability of this ability into RL agents? Can we sort of learn some kind of representations only from the state action, just task-independent transitions, which allows us to get optimal policies, zero shot, that is without any further interactions, for a whole lot of tasks, a whole lot of rewards, or like anything in the environment. Taking a step back, I'd like to explain how we can do this. I'll introduce this quantity called visitation distributions. So suppose your agent is at a particular state that's sampled from some initial distribution. It follows a policy and executes a trajectory. The trajectory looks something like the state, action, next action, and so on. The probability of being in a particular state and action in this trajectory is called the state action visitation distribution, and it's given by this a cumulative sum of the probabilities of the agent being in different states at each particular time step. A similar quantity called successor measures can be defined, which generalizes over visitation distributions in the sense that now, instead of assuming that I'm starting at an initial distribution, I can start from any state and any action and find out the probability that where I'll be in future. So I introduced saying that the topic saying that I'm trying to represent all possible solutions of RL. Now, what does it mean to have a solution of RL? We represent solution of RL in terms of visitation distributions. So the RL objective that I initially introduced can be rewritten in this linear programming form that's an equation on visitation distributions. Now you have got you want to maximize the dot product between the visitation and the reward such that the visitation follows this equation. It's constrained to follow this complex-looking equation. But if you look closely, it's nothing but the Bellman equation. So for all visitations that follow the Bellman equation, you want to find the one that maximizes the reward. This is essentially the RL problem. And similarly, you can also define a linear program for successor measures if you replace visitation distributions with successor measures over here. So let's go into representing all possible solutions. If we have a linear equation, AX equals to X naught, we can say that any solution of this linear equation can be represented using a basis and a bias, just simple linear algebra. And this means that every solution of this linear equation can be mapped to a particular space using a set of affine coordinates. If you look closely, the Bellman flow equation is also linear. So that means any visitation distribution, any successive measure can also be written as a linear combination of certain basis and a bias. So this is the crux of representing all solutions, that if we are able to find out this basis and bias, then we can then any possible task in the dynamics can be represented using this linear basis. using this linear coordinate. So what does this overall procedure look like? I have an environment. From this environment, I don't have a reward. I just have the dynamics. I have task-independent, reward-free interactions. From that data, I obtain this polytope, this plane of the affine plane that represents all solutions. Within this affine plane, there exists this convex hull, which gives the valid solutions, because additionally, these solutions, like the visitations, need to be valid. They need to be positive. And once I get this solutions polytope, any policy in this polytope is represented using a linear weight. So given a reward, given a task, all I need to do is search within this convex polytope. And as you can see there, the procedure will have 2 phases. The first phase would be something like a pre-training where you obtain this polytope. And in the second phase, inference for any reward, any task, it's just a linear search within this polytope. Getting a little more, to save time, I'll just skip this and quickly get into the results. So initially in the environments with such as grid world and in mazes in a manipulation environment, we can see that this method not only is able to solve any task, it solves tasks better than the previous unsupervised methods. And also, it can be seen in the continuous domain Mujoko task, where for each environment you can define, like for each dynamical system, you can define different forms of different tasks. For Walker, you can define running, standing, flip, and all sorts of things. And for all of them consistently, we can obtain the optimal policy compared to the previous methods that try to learn some kind of a span or eigenvectors or stuff like that. The key takeaways would be that we can represent all behaviors of an RL agent in an affine space, and this plane can be constructed using just reward-free interactions. And further, once the polytope is known, optimal policy for any task using any optimization criteria. So for these set of experiments, I used a reward maximization criteria for defining an optimal policy, but for any imitation learning, inverse reinforcement learning, any of them, you can come up with the optimal policy in a very quick way. And I'll end up with a simple application that's under review right now. So what we did was, we learned the same solution space for these environments, but instead of using the reward maximization, we used language models and like video language models to define optimality. And so for different language instructions or mimicking an image or a video, you can see that you can just generate these optimal policies for these different tasks, like zero shot, without any interaction from the environment once you have learned the solution space. Yeah, that's all.
We have time for 1 or 2 questions.
We're going to find out if I followed that well enough or not. If you're not offering a reward at intermediate steps, the more number of tasks you have, you're increasing the complexity of possible solutions rather drastically. The more complex the task is, right?
As I said, there are 2 phases of it. Once in the first phase, you're trying to just represent the solution space. That's the space of all possible Markov policies in the dynamics. Next phase is when you do the inference, when you find out the optimal policy. So that's when you provide rewards. That's when you define the problem, saying that, okay, now the optimal policy is defined, say, a policy that maximizes a value function, maximizes a value function, maximizes the expected sum of returns.
That leads me to a second question then, if I understood quickly. Does this approach reduce the probability of finding novel solutions?
If you can define a reward, then what do you mean novel solution? If there's a reward, there would be an optimal solution for that.
Yeah, I suppose so. I guess I'm trying to wrap my head around if there's not the intermediate state reward.
So ideally, if
Yeah.
you're thinking a sparse reward, like a setting where you're just giving reward at the very end, and would it be able to recover rewards intermediately? So with this
Sort of
method,
turning it down a path, right?
so with this method, because you are representing all solutions, when you provide a very sparse reward, saying that, okay, I provide a reward at the end only if I visit a particular state or something like that. Now, when you do the linear search, when you search, do the inference using the reward, using this reward function, and what would it do? It would find out the policy, the visitation, that already optimizes this reward. So it would find out the policy that even in a sparse reward setting, that does the task,
Okay.
that solves the task optimally.
Thank you.
Thank you, Siddhant. Okay, last but not least, we have Max Rudolph. Max is a PhD student at UT Austin, advised by Amy Zhang, working on deep reinforcement learning. He is supported by the NSF Ethical AI Fellowship. He is interested in all sorts of deep reinforcement learning problems, but recently has been thinking about self-supervised learning within decision-making contexts. Max graduated with his bachelor's and master's in electrical engineering from Georgia Tech in 2021, where he worked on multiple robot systems and sim-to-real for navigation. Please join me in welcoming Max.
All right. Hi, everyone. Thanks for sticking around. So my name's Max. I think the title that she just said is slightly different than the title I have up here. That's because I changed the title a couple minutes ago. But I'm going to be talking today about reevaluating deep reinforcement learning in two-player zero-sum games. This is work done, a large collaboration with, I guess, myself and everyone here, and Nathan, Shoban, Alexander, Zico, Amy, Gabriella, Eugene, and Sam. A lot of people. We had to, in our meetings, that's how we'd introduce ourselves. But anyway, so in general, we're interested in multi-agent problems. And right now I'm going to talk about multi-agent robotics problems a little bit. So in general, when you think of these sorts of problems, you're talking about making decisions when there are other decision makers present. And I think Kyle and Arthur's work really touches to this when you're trying to coordinate with humans or you have to navigate around humans. But I'll talk about that in a moment. So let's look at on the left side of the screen here, you have cooperative problems. You have an Amazon warehouse where robots are cooperating with each other. Excuse me, and you have autonomous driving, where you have to not crash into other people. These are decentralized cooperative systems. On the other hand, you have something called adversarial systems. So that is an air hockey playing robot, where you're trying to, basically your reward is someone else's cost and vice versa. Now we can further dive into adversarial games where we have perfect information, where I know where the puck is, I know where that other robot is, and then we have imperfect information, where who's played poker? Okay, yeah, that's an imperfect information game where you don't necessarily know the state of your other agent, but you're still trying to act optimally. So right now we're going to deal with imperfect information adversarial games, but you'll see why that's relevant to any of this. So imperfect information games are somewhat ubiquitous. So if you're familiar with the prisoner's dilemma, where you're trying to decide whether to give up your cellmate or not, this is an imperfect information game. And when you have small games like that, it's relatively easy to solve them. You can use some linear programming, whatever solver you like, and figure out like the optimal solution. So in small form, they're solved. The other thing is imperfect information games are also pretty commonly played, whether you know it or not. So adversarial robustness in machine learning is an imperfect information game. Any driving problem really could be cast as an imperfect information game, and goal seeking and all these things are imperfect information games. Hopefully that drives the point home. Okay, well, that seems to be skipping over, but what that was going to show was some of Arthur's work, in fact, can be recast as imperfect information games when you are trying to figure out how to coordinate with a human. So to give you a quick introduction to what we're dealing with here, we are trying to use reinforcement learning to play games optimally, and I'm using game in a very abstracted sense. So the goal is to learn some policy pi I, that refers to my player, to play this game. Some reward I, sorry, I don't know what's going on with the sequential thing here, but some reward I, and necessarily my reward plus your reward will always equal 0 across all time steps. And we're going to deal with large imperfect information games like poker, but not like tic-tac-toe. So when you like naively apply reinforcement learning like Siddhant was mentioning to these games and you have them just play against each other, what will happen is you play together and then they'll collect data, they'll update their policies and go through this loop over and over again. But this actually leads to some really undesirable behavior. So if you're playing something very, very simple like rock, paper, scissors, what will happen is your strategy, if you follow this method, what will happen is you will always be trying to respond best to your opponent. So if your opponent keeps playing rock, I'm going to keep playing paper, and then I'm going to keep playing scissors, and we have this spiraling behavior that's very undesirable and leads to like highly exploitable policies. Meaning, if you just stick to one of these, you're going to you can well, be exploited very easily, and you'll lose a lot of reward. So this is not ideal. But luckily, there are some solutions to this in the field in the form of these 3 general algorithm classes. Don't worry about what those actual diagrams are. It's not that important for this talk. But there are 3 main sections: double oracle, fictitious play, counterfactual regret minimizations. But the problem is they all have this, like, one of the 3 or 2 of these 3, like, very undesired properties. They converge really slowly for reasons I won't go into. They have a complex representation of the policy, which for reasons I won't go into, and or you have to deal with complex, like importance sampling over these trajectories. In general, this is not very desirable. So, okay, I've said mostly bad things so far, but hopefully I'm going to turn the corner and then we'll say some good things about some other algorithm. So let's say we wanted to revisit self-play, and some of my collaborators did this about a year or 2 ago. So they introduced this algorithm called magnetic mirror descent that adds some properties to this self-play algorithm that actually performs quite well. So this is Sam Sakota was the first author here, and he is the author on this paper, so you could see the inspiration here. But essentially, what I'm showing here in blue is, so lower here is better. The performance of magnetic mirror descent, this new algorithm with these properties, actually performs much better than the alternatives like fictitious play and the naive self-play versions, which are both in orange and green here, respectively. So magnetic mirror descent has these properties, like 3 main properties in red, green, and blue here. Again, the math is not super important. What the colors mean is we want to, 1, maximize our reward in these adversarial games. We want to, 2, control the update size. So we don't want to move too far away from our previous strategy or policy. And then 3, we want to add some random bonus, some entropy bonus to our policy so that no one can really, abuse a policy because the policy itself might not know so much what it's doing itself. That's a little hand-wavy, but it works. So we're curious whether, and this works in self-play, so we're curious, like, is this unique to magnetic mirror descent? These 3 properties. So there are a lot of RL algorithms that people have sort of pushed by the wayside in self-play because self-play doesn't work, right? But when you have these 3 properties and you scale them correctly, it turns out that maybe we should revisit this and work. So what we want to do is let's benchmark these algorithms, like very rigorously, very thoroughly, to see how we can scale these 3 properties of arbitrary algorithms to see how well self-play actually performs. So that's a bench, and we're going to benchmark. So like a very simple thing we want to do is we want to benchmark across tons and tons of hyperparameters. And here tons and tons means thousands and thousands. So we'll pick 7 representative algorithms here and play 4 different games. So these 7 algorithms, we will sample thousands of hyperparameters for all of them and just run these algorithms and see how they perform. This gives us a sense of how good are these self-play algorithms when they're tested properly. So the key thing here is once we have these good hyperparameters, or we have a big representative set of hyperparameters, we can retrain our algorithms on the best sets of hyperparameters. Now, this is not too novel. Like, this is a pretty common idea that anyone here could come up with. But what we find is that when we retrain the top N, it's actually top 50, or yeah, top 50 hyperparameter sets, these self-play algorithms perform much, much better than these tailored, undesirable algorithms that I was mentioning earlier. And this is novel because we're doing this very, very wide sweep of hyperparameters on algorithms that people thought were dumb to start with. And so you can imagine that if people have this notion of what these algorithms should be, and then you benchmark against those algorithms in previous papers, okay, let's just say this algorithm is bad and let's forget about it. That's not the case in reality, and this is what we're showing here. So in these blue dotted lines, we're showing, again, lower values are better, less exploitability. So very briefly, I want to give, so this has been a very sort of hand-wavy talk, but I want to give some like very high-level takeaways. So we find that this magnetic mirror descent, or otherwise known as like a regularized policy gradient algorithm, it outperforms all of these multi-agent specific algorithms on the games that we test. And this is a very, very new thought, surprisingly, that not many people have had. And it's surprising to, sorry, I won't complain why, I won't describe why it's surprising. Let me keep going. So what's really important is this is a step towards a more unified set of algorithms for multi-agent, 2-player settings. And why it's important for robotics is because now you can't do these sorts of benchmarks when you are dealing with Arthur's problem, for example. You want a good algorithm that works on finding how to coordinate a human and a robot, and you can't run thousands and thousands of trials like we do in this set. But this work is like taking a step towards, excuse me, taking a step towards this universal algorithm that we can apply to arbitrary robotics problems without having to go over and over and test. So I think that's my last sentence. So I will thank you for your time. Yeah, thank you. Yes.
Is exploitability as a metric sufficient to describe the whole outcome? If you've got lower exploitability, your outcome is good, or there's some other ways you can do different metrics you can look at?
Yeah, so that's actually another part of this work. So exploitability is like the de facto so how do you measure how good you are at playing a game? Yourself, you can't do it because you don't have another policy to test against, right? So let's say we train another policy. Okay, you're performing well against this other policy, but that's not really telling you much because you're only testing yourself against another strategy. So exploitability is a very common metric that people use, and I believe a good metric because it is telling you how much will you lose if you are playing against a worst case adversary. So how worse can you be exploited? Yes? So the answer to your question is no and no, but more nuanced, you can recast a lot of multiplayer games as 2-player games, and you can recast a lot of general-sum games or general-sum games as zero-sum games. So this is why it's relevant just generally and more abstracted. Thank you. Okay. Do I have time for one more?
If it's quick.
A quick one. I'll give a quick answer, too.
Can exploitability be a positive in human interaction so that a human could know quickly how to get what they want, whether it's what the robot wants or not?
I don't know if I fully understand your question, so I'll take it offline. I have a poster later, so feel free to come ask questions. Thank you.
See you there.